I executed the MapReduce job on my local machine, but when I was doing the hands-on for HDFS, I had to create an EMR cluster. And as you have already seen, that EMR cluster contains multiple nodes. You can create the number of nodes of your choosing. So what would be the master node and what would be the different compute nodes? So you can imagine that it is a cluster. Cluster is a grouping of nodes. All of the big data work that we do has to be done on a cluster. We can learn using our local machine, using our laptop, or using a single EC2 instance. But whenever you do any POC in the development environment, or whenever you do any unit testing, system testing, integration testing, etc., it has to be done in a cluster, because the big data framework, irrespective of the compute framework or data processing framework, all of them run on a distributed system, which is a cluster. And cluster is a grouping of one or more machines. Like here we have a master node. I'm naming it as node 0, and then we have follower nodes with node 1, 2 and 3. Now whenever we run any data processing code using frameworks like MapReduce or Spark, what we do is that we write the code and then we submit the code to the main master node. And in HDFS or Hadoop lingo, you know that the master node contains something called name node, and it also contains something called resource manager. And this master node has to send the code to all of these follower nodes or the compute nodes, where the code would be executed, because the data is scattered across all these nodes. So when you are submitting one code or one application, that is fine. What if you have multiple applications? All of them have to be submitted to the master node, and the master node has to decide where to execute these codes, these applications. Now this is a very tricky stuff. It is not as straightforward as you can think, because here I'm showing you only 3 applications that is running MapReduce code. So imagine you have multiple Spark codes that are also running, or Hive queries that are running in this particular node or in this particular cluster, and there are maybe tens of compute nodes, let's say 40 to 50 compute nodes. So it's a very tricky task to assign resources to these applications, because Spark would need its own resource. By resource I mean CPU and memory. MapReduce would need its own CPU, memory and network bandwidth. So would Hive, and so would any other distributed processing framework like Flink, Flume, etc. What Hadoop did, Hadoop offloaded this particular work to another component called Yarn, and the full form of Yarn is yet another resource negotiator. So if you look carefully at the name says it is a resource negotiator, and that's all it does. Yarn is a software component, or is a software that runs across all the nodes and allocates resources to these applications. These applications can be MapReduce codes or Spark codes or Flink application or Hive query language, anything. So the allocation of resource would be done by the component named Yarn. And Yarn supports multiple distributed processing framework, which includes Spark also. That is the reason I'm talking about Yarn here, because when we submit Spark job in either EMR cluster or in Dataproc, Yarn would be used to allocate the resources for those application codes. Now let's look at the anatomy of Yarn, how or where it sits. We have this distributed storage. It can be HDFS, which is attached storage to the compute nodes. If we use AWS, it would be EBS volumes to the EC2 instances in EMR cluster, or it can be distributed storage like S3 or GCS also. Then you have distributed processing framework like MapReduce and Spark. And then we have this cluster, and this cluster contains one master node and multiple follower nodes. In case of EMR, that is compute node. We can also have something called task node. And this cluster would be communicating or talking to the distributed storage. If it is HDFS, the storage would be assigned or attached to these individual nodes. If it is cloud storage, then it would need API to communicate to the cloud storage or cloud data lakes like S3 and GCS. Now what we have to do is that, let's say we have written MapReduce code or Spark code, and we'll have to submit the MapReduce code or Spark code to the cluster. And that's where Yarn takes the place. So yarn sits in between the cluster and the application code that we run, and yarn manages the resources in the cluster for these applications. So what we do is that we submit the code to yarn, either it is MapReduce or Spark or Hive query or Flink or any other distributed processing code that we write. We submit it to yarn, and yarn negotiates the resources, which is CPU and RAM, that is needed for these applications. So the main job of yarn is to find resources to run the application. And as I already mentioned, resource is nothing but compute, which is CPU and RAM. Now the question is, where do you place yarn, or where do you keep yarn? Should we keep yarn in a separate cluster altogether or in a separate machine altogether and then ask yarn to manage the resources here? Or should we keep it in the cluster itself, in the cluster where we are going to run the distributed processing and which is attached to the distributed storage? So what happens is that keeping yarn in a separate cluster can be plausible, but that has a little bit of overhead. So the components of yarn or the yarn software by itself are installed in all the nodes of the cluster. So if we have one master node and let's say 20 compute nodes or follower nodes, then the yarn components would be installed in the master node and all the 20 compute nodes. So that brings me to the yarn architecture. So we have to know how yarn works. So this is our cluster. We have one master node, which is node 0, and then we have multiple compute nodes where the distributed processing would run, and they are connected to each other over the network. The component that is installed in the primary node or the master node for yarn is called resource manager. So this is the component of yarn which is installed in the primary node or the master node. And in the compute nodes, the component of yarn that is installed is called node manager. So the resource manager component would be there in the primary or master node, and the node manager component would be there in all the compute nodes or task nodes in case of EMR. Now, what does yarn do? Does it only sit there and allocate resources? It does a little bit more than that. So what yarn does, the individual components rather in the compute nodes, is that it breaks a single node into multiple small computational units. What I mean by that, let's take an example. So let's say for our nodes, the single node configuration, we have a total vCPU of 32 and a total memory of 512 GB. So what yarn would do, yarn would break it into pieces and create a small logical block with 2 CPU and 32 GB of RAM, or 2 vCPUs and 32 GB of RAM. So you can imagine that each compute node can contain 16 of such small blocks. We can call these blocks as smaller virtual machines also, but yarn calls it as containers. So these containers would be created in all the different compute nodes that we have. It will not be there in the primary node, it will be there only in the compute nodes, because the application code or the distributed processing code that we run or that we want to execute, either it is MapReduce or Spark, would be executed in the compute nodes, not in the primary node or master node. So that's why the containers would be created in the compute nodes. And each container would contain 2 CPU and 32 GB of RAM, or each container would be allocated 2 vCPU and 32 GB of RAM. So you can imagine that each node would contain 16 such containers. And these are the small computational units that are created by yarn. Now the obvious question would be, why do we need such small computational units? The reason is that a single node, let's say, would contain a large amount of CPUs and large amount of memory, and would be running multiple applications, right? So would be running Spark application, would be running MapReduce application, or any other distributed processing framework that we want to run in the same cluster. So if the node is not broken down into small pieces, what would happen is that a single application might attach itself to all the resources that is available in these individual nodes. Meaning that, let's say you are running a single Spark application or you have submitted a single Spark application, and that Spark application is running in all these nodes, if there are not smaller computational units, that Spark application would consume entire 32 CPUs and 512 GB of RAM, even if that application or the Spark code does not need it or does not need so much of resources. So that's why what Yarn does, it breaks a large server or a node into small computational units so that the allocation can be done using these small units. If a Spark application, let's say, needs more compute, then more of these containers should be allocated to that application if available. So that's what Yarn does. One of the very basic tasks that Yarn does, the moment we install Yarn and its components like resource manager in the primary node or master node and node manager in the compute nodes, Yarn would essentially break this entire server or node into small computational units called containers, which would be allocated a certain amount of CPU and a certain amount of memory of the entire node. Now, if you talk about resource manager, it manages the use of resources across clusters, and node manager launch and monitor these containers. These are the purposes of resource manager and node manager of Yarn at a very high level. Resource manager would manage the use of resources, meaning that how many containers should be given to a single application, and node manager will launch these containers and monitor whether the containers are running, whether the execution is done, whether the container has failed, so on and so forth. So that is the purpose of Yarn, and that is the purpose of individual Yarn components like resource manager and node manager. So this is the Yarn architecture at a very high level. I'll not be doing any hands-on using Yarn because we'll be using either EMR or Dataproc. So it does not make sense to spend a lot of time in configuration and installing Yarn. We'll not do that. So that's why it will be only theoretical. Now, after talking about the architecture of Yarn, let's understand the application flow. So what happens whenever we submit an application like a MapReduce code or a Spark code? So again, we have the same cluster. Node 0 is the primary node or master node. Node 1, node 2 and node 3 are the compute nodes, and it has Yarn components installed in it. Node 0 contains resource manager, and node 1, 2 and 3 would contain the node manager components. Now what would happen in the compute nodes? Node manager would launch containers as and when needed. It would not allocate containers beforehand. Whenever we submit an application, then only these containers would be allocated. But for simplicity's sake, I'm showing you that the containers are already available and then we submit the application. But this is not how it happens. Whenever you submit an application, then only the containers would be allocated to those application codes. The containers would be launched and allocated to those applications. So let's say I have written this application code. It can be MapReduce or Spark, and I submit it to the resource manager. This is step number 1. So this round circle contains the step number. So this is the first step, that we submit the application code to the resource manager. Then what resource manager would do? Resource manager would try to find out one of the node manager which is available, which is not that busy. So it might be the case that some other application or some other Spark code is already running in this cluster, and we are submitting a new Spark code or a new Spark application to the resource manager. So resource manager would find out one of the node managers which is not that busy. If none of the node managers are available, then the application code will have to wait. So then the application code would actually talk to the resource manager, and let's say the resource manager has found the node manager in node number 3, which is less busy or which is available. So what the resource manager would do? The resource manager would submit or create a container and run the application master in that container. So what is application master? In Spark, it is the driver code. I'll talk about driver later on. And in MapReduce also, we have something called application master, which will actually run the distributed computing framework in all the other nodes. Now, this is the primary component of the code which is handled by the framework. So when I wrote the MapReduce job or MapReduce script using Python, I did not mention any application master because that is automatically handled by the framework. And the purpose of application master is to communicate and track the execution of the application code that would be running in the other containers. Okay, anyway, this is the third step, that the node manager would launch the application master, and then the application master would talk to the resource manager and it would ask for more resources for the application code to run. Now, why that is the case? Because whenever we submit a job, whenever we submit an application, let's say Spark application, we mention the amount of memory and the amount of CPU that we need. If we do not mention anything, the default number of CPUs and the default number of, or the default amount of memory would be used. But we can mention that we need this many number of CPUs and that this much amount of RAM. So based on that, the application master would talk to the resource manager saying that I need more resources to run the application code, which is actually the transformation code that we have written. In case of MapReduce code that I had shown you in the hands-on, it would be maybe a select, creating the map and key, etc. Then a resource manager would again check whether there are enough memory and CPU available in the cluster or not. If it is available, then it would launch the remaining application code in the compute nodes. So here in step number 5, what it is doing, it is asking the node manager to launch the containers and run the application code which has been given by application master. And it would only be applicable if the resource is available. If the resource is not available, then obviously the code has to wait, or the application has to wait for the resources to become available. Right. So this is how the application flow is, and then the application code would run. The application code would communicate to the application master, and it depends on the framework that you are using. If it is a Spark framework, then these are called executors. The executors would talk to the driver about their status of the execution and a few other things. And then when the application execution is complete, all these containers would be terminated. Okay, again, let me repeat. What happens is that we run or we submit the application code to the resource manager. This is the first step. And in the second step, resource manager finds one of the node managers if there are resources available. And if the node manager is not busy, that is the second step. In our case, let's say this node manager is not busy, and then the resource manager would ask the node manager to run the application master. In case of Spark, the application master is called a driver. We'll talk about driver in our Spark discussion anyway. Then what happens? The application master communicates with the resource manager to bargain resources that it needs to execute the code. It can be MapReduce, Spark, or any other code for that matter. If the resources are available, then resource manager would ask the available node managers to launch the application code in the container. So the containers would be launched and the code would be executed in those containers. And you already know what containers are. Container is a small computational unit which contains certain percentage of CPU and RAM of the entire node. And once the execution is complete, then all these containers would be terminated and the resources would be made available again, the cluster resources, that is. So this is how Yarn application flow happens. And do not confuse the container with Docker container. This is not a Docker container. The term container here is used by Yarn. I hope you have understood the purpose of Yarn. The first thing is that it breaks down the compute nodes into smaller computational units called containers. And then the major purpose of Yarn is to allocate resources and run the distributed processing framework like MapReduce or Spark. Now the question is how Yarn does this resource management and allocation of resources or creation of containers. It uses a lot of configuration variables to achieve this. And the configuration file of Yarn is yarn-site.xml. You do not have to worry about, or you do not have to configure too many things in the file, because in most of the cases we would be using the default configuration variable and its corresponding value. But there are some configuration variables which are important and we should know as a data engineer. And those are these. On the left hand side, you have the name of the configuration variable, and on the right hand side, you have the description of what this configuration variable does. The first one is yarn.scheduler.maximum allocation MB, and it tells you the maximum memory that can be allocated to a container. So let's say if you have 512 GB of memory, you say that the maximum allocation MB is 50 GB. That means a container cannot be created with a memory more than 50 GB. If you try to create a container with 64 GB, either it will fail or the amount of memory would be reduced to 50 GB. So this is the maximum memory that can be allocated to container. Likewise, you have yarn scheduler maximum allocation vcores, which is the maximum number of vCPU that can be allocated to a container. Similarly, we have minimum allocation MB and minimum allocation vcodes, which is the minimum memory for a container and minimum vCPU for a container. Right, so this is the range between a minimum allocation MB and maximum allocation MB. So this is the memory range, and minimum allocation vcodes and maximum allocation vcodes are the CPU ranges. So using this, you can configure the minimum and maximum CPU and RAM that can be allocated to a container. Then we have yarn.node-manager resource memory MB, yarn.node-manager resource CPU vcores. This is the allocated memory for a container. Now let's say you need to create a container with 10 GB of memory, then it would be allocated. If that much amount of memory is not available in the cluster, then the container has to wait. The creation of the container has to wait. Same is the case with CPU vcores also. And then I have also mentioned something called increment allocation MB and increment allocation vcores, which is the incremental step for container memory. So if you are using dynamic memory allocation, let's say, then how much memory would be added to the container if it needs more memory or more CPU? What is the number of vCPU that would be added to the container if dynamic resource allocation is used? Let's take an example to understand this. So let's say I have this node whose total available memory is 512 GB and total available vCPUs are 32. So this is the total memory and total number of cores in a particular node. Obviously, there can be multiple other nodes also. And let's say this is our yarn configuration. Scheduler minimum allocation MB is 16 GB. Maximum allocation MB is 64 GB. Minimum allocation vcodes is 1 and the maximum allocation vcodes is 4. And we have this node manager configuration wherein the resource memory MB is 32 GB and resource CPU vcodes is 2. Meaning each container would contain 2 vCPUs and 32 GB of RAM. Let's say you are running a MapReduce application which needs 10 containers. So we'll track the available CPU and available RAM here. And because all the memory and CPU are available in this particular node, all those containers would be started in this node. So from container 1 to container 10, all would be running. Now, as you already know that the amount of memory for each container is 32 GB and the amount of CPU that each container has is 2. So the available vCPU is 32 minus 20, which is 12, and the available RAM is 512 minus 320, which is 192 GB. Now let's say another Spark application comes which needs 10 containers. Now, as you can see that we cannot launch 10 containers anymore in this node. Rather, yarn cannot launch 10 containers. So it would launch only 6 containers and the other 4 containers would wait. Why it would wait? Because there's no available memory anymore and there's no available vCPU anymore in this particular node. If there are memory and CPU available in the other nodes, then those 4 containers would be launched in the other node. If you use something called dynamic resource allocation, in that case, let's say if one of the containers or a few of the containers need more memory and more CPU, a single container cannot have more than 4 CPU and more than 64 GB of RAM only if the memory is available. So now let's say I have not launched this 6 containers and container number 9 and 10 need more memory and more CPU. So now container 10 can be allocated a maximum of 4 CPU and a maximum of 64 GB of RAM. Same would be the case with container 9 also. So after that, the available CPU would be 8 and the available RAM would be 192 minus 64, which is 128 GB. So this is how the resources are allocated by Yarn. The allocation is handled by the resource manager, because resource manager would see where the available CPU and RAM are there, which node manager can handle it, and then resource manager would communicate to the node manager saying that I need so much amount of CPU and so much amount of RAM for each container, and I need to launch so many containers. And this allocation request would come from the application master. In case of Spark, that would be the driver node, and in case of MapReduce also we have application master. So application master would say that I would need so much amount of memory and so much amount of RAM to the resource manager. Resource manager will check the availability and then ask the node managers to either launch new containers or increase the resource within the available containers itself. So this is how Yarn works.